In this section, we will finally define the real numbers. As I've already mentioned in the previous video, we have now ordered fields. We have the field axioms, we have the ordering axioms, but it's still not enough to determine the real numbers. So in this section, we will introduce another axiom, which then settles the debate. To do so, I need to introduce some additional notation for ordered fields, or some additional terminology, to be precise, for ordered fields. Definition 141. Let K be an ordered field and A be some subset of K. Okay, recall we have a total order on K, and we then use this total order, which I always denote by this smaller than or equal to, as I did before. First of all, the set A is called bounded from above. Above. If the following holds, if there exists an element of the field, I will call C, such that A is smaller than or equal to C for each element of A. So the same C for all elements of A. So C is then what we call an upper bound. So C is then called an upper bound for A. And so we've got, so one element such that everything lies below. That's the idea here. The same thing we can now do the other way. We can call A bounded from below if there exists some element I will call B in K such that, and now the other way around, B is smaller than or equal to A for all A in A. So there's one element of the field which is smaller than or equal to every element of A. So this is then, one element which is smaller, and this element, smaller or equal, and this element is then called lower bound. For A. Okay, same construction from the other side. So of course I say A lower bound and not the lower bound because it's not unique. I mean everything, if some element B is a lower bound and we have another element which is smaller than or equal to B, this is again a lower bound for A by transitivity of this relation here. So we have many lower bounds then, potentially. Okay, so much for that. So this is bounded from below, bounded from above. And as I said, we have many upper bounds or lower bounds usually, but we want, of course, we're interested in what's the best upper bound or the best lower bound of a set. And by this I mean the following. We call an element S in K is called the smallest upper bound for A I messed up my grammar. It's not, something was not sounding right. Bound of A would be the correct English. I'm sorry about that. And the same here. To satisfy all the grammar freaks in the audience, I'm sorry about that. Smaller bound of A. So it's the smallest upper bound of A. First of all, if it is an upper bound, is an upper bound of A. And now the additional property, every possible upper bound is S or bigger. So this is what we say by intuitively this is the smallest upper bound. So for every and S is smaller than or equal to C for every upper bound C of A. So here this is what we say by the smallest upper bound. And of course we can do the same thing with upper bounds. with lower bounds. Some element I would call I in K is called the biggest lower bound of A. Biggest lower bound of A if I is, first of all, is a lower bound. Of A, and B is smaller than or equal to I for every lower bound B of A. Oops, lower bound B of A. Okay. Yeah. So much for that. So we have this notion of biggest lower bound, smallest upper bound, but of course this is just a definition. So in general, we don't know if these things even exist, if there is something like a biggest upper bound or if there is a smallest upper bound, and we will see in a moment that this indeed is not always the case. Okay, first of all, some remark. We will encounter these smallest upper and biggest lower bounds quite sometimes during this lecture in some special context that we will see later. And the thing is now, how can we check that some upper bound is really smallest upper bound, or in the lower case analogously? So how can we check that every upper bound is indeed bigger and to bigger or equal? So to really do this, there's a nicer, I'd say a nice criterion, namely for the following: some element S star is the smallest upper bound of A if and only if it's an upper bound, is an upper bound of A, and every value below is not an upper bound. And this is what we want to formalize now. So for every element which is smaller, strictly smaller than S star, this is not an upper bound for A, and upper bound means everything lies below, and if it's not an upper bound, some element has to lie above. So this means for each such element which is smaller than our, supposedly the smallest upper bound, there exists an element A of our set A which is too big. So with A is bigger than S. And this is something you can check. So this is something that's usually, you take any number which is smaller than your favorite number that you want to check to be the smallest upper bound. Then you can find some element of A such that this holds. So this is something you can explicitly compute. And to show that something is also, if you want to show that something is not an upper bound or something, not a smallest lower bound, you can kind of contradict this or something. So there are several ways of making use of this. Analogously for the lower bounds, for completeness, I will write this down in full detail. So some I star is the biggest lower bound of A, if and only if it's a lower bound. I star is a lower bound of A, and every element which is bigger than I star is not a lower bound. So for all I bigger than I star, there exists an element of A which lies below. So this cannot be a lower bound. So there's there exists an A in A with A is smaller than I. So completely analogous to the upper bound version. Okay, now you can see both blackboards. So this is kind of the way I've used it. We will see some examples in the exercises of this. So much for this remark. Then, as I said, the existence of smallest upper bounds or biggest lower bounds is not guaranteed. Of smallest upper, biggest lower bound is not guaranteed. And it's a simple example. We have considered the ordered field of rational numbers Q, and we can easily write down a set which does not have a smallest upper bound in Q, namely the following: x in the set of all x in Q such that x squared is smaller than 2. Okay, what's the biggest, the smallest upper bound? The smallest upper bound would be the number where we get equality here for this computation, and which is so a positive solution of this equation x squared is equal to 2, and as we've already discussed, there is just no rational number. And this is precisely the phenomenon that some numbers are missing here in Q that we want to be part of our real numbers. So this set does not have a smallest upper bound. So this is kind of a formal or a kind of a translation into really precise mathematics that some of this fact that some numbers are lacking in Q. So the Q is not big enough for our purposes. And this is now the motivation for how to define the real numbers, or for how to tackle them. Namely, we make this property that we want. So of course we want that these upper bounds, smallest upper bounds exist, and same for lower bounds. And there is a simple notion that makes sure that this holds. Namely, an ordered field K is called complete if every subset, every A subset of K that is bounded from above has a smallest upper bound. So this example shows that Q is not complete. This is the problem here. So the idea is now we assume completeness. So we want a field which is ordered and which is complete. And then it turns out there aren't that many. There is basically only one. And this is a theorem which is kind of very deep and very abstract. And so I will not make this a combination of theorem and definition. You will see why in a second. 144. So the idea is here, up to, and now I'm very imprecise by saying equivalence. The notion, mathematically correct notion would be isomorphism of fields, but this doesn't matter here. Up to equivalence, there exists a unique, complete, ordered field. So up to some isomorphisms, but essentially so the idea of this thing is now all complete ordered fields look the same. And this is now, we can just discuss this as if there was just one. We can forget about the equivalence. So essentially there's only one. And this field, and so this was the theorem part, and now comes the definition part. Call this field the real numbers. Denote it by R, as we know from school. So finally, we have a formal definition and construction of all of the real numbers. So I will not prove this theorem. If this was a course for really pure mathematicians, I would do this, but for you, it's not really relevant. I mean, there's some kind of technical thing. It's not that easy, but so this is just important. There's only one such thing. So we have we first have the field axioms. So we have addition and multiplication. They behave nicely. Then we have the ordering. And then we additionally have to assume this completeness. So this existence of smallest upper and biggest lower bounds. Then we're done. Then we've got the real numbers uniquely determined. And that's the important thing here. So first of all, some first consequence and some first property of the real numbers. So we know that every subset bounded from above has the smallest upper bound. The question is, of course, why, if we say we want a complete field, why don't we demand as well that every subset bounded from below has a biggest lower bound? So just the other way around. The answer why I don't, to the question why I don't demand this here is because it already follows. Because here we already get, if A is a subset of the real numbers which is bounded from below, then it already follows that A has a biggest lower bound. So it's indeed enough to demand the existence of smallest upper bounds to get all upper and smallest upper and biggest lower bounds to exist. Has the smallest lower, biggest, shouldn't talk and write at the same time. It's, yeah, sorry. Has a biggest lower bound. Okay, this follows automatically, but for the proof of this, I have to quickly erase the breakboard. Okay, we want to derive the existence of biggest lower bounds from the existence of smallest upper bounds that we have assumed to be true in R. So we start with a set A, which is bounded from below, and we define another set, and which I call minus A, and this should be the set of all elements of the form minus x, which is also a real number since R is a field, for all x in A. So we just flip the sign of basically of all of A. So this has a nice consequence. If B is a lower bound of A, which means that x is bigger than or equal to B for all x in A, then we know that putting a minus sign in front of both things flips the direction of the inequality. This was part of this theorem with properties of ordered fields. Then minus x is smaller than or equal to minus b for all x in A. So I will add this again. I've already put this in the lecture notes. This was theorem 138. Whoops. Okay, so we have this property. But what does this say? This says that minus b is an upper bound for minus a. So we know that a is bounded from minus a is bounded from above. But this means we have a bounded set from above and we are in the real numbers, so we know that this has a smallest upper bound. Has a smallest upper bound Sorry for the cut, I just messed up one part of the proof and just want to redo it again to have this properly. So we have a smallest upper bound, we call the small s in R. If we have this, we know that, first of all, it's an upper bound. So minus x is smaller than or equal to s for all x in A. Which in turn implies, by again using this method of sign flipping and doing this trick again, that if you put a sign on top, the direction of the inequality changes. X is smaller than, is bigger than or equal to, minus s for all x in A. And this means that minus s is a lower bound for A. Just by definition. So, the idea is now that we want to show that this is indeed the biggest lower bound, and there's no bigger one than minus s. Suppose we have a bigger one. Suppose there exists some lower bound A of A, which is bigger than this one, so with A bigger than minus s. So, since this is a lower bound, we know that x in x is bigger than or equal to small a for all x in A, which in turn means, by this sign flipping thing again, minus x is smaller than or equal to minus a for all x in A. So minus A is an upper bound for minus A. An upper bound of, again written for, sorry, of minus A. But this is a contradiction. And the contradiction we always denote by this lightning crashing in. Namely, why is this a contradiction? Contradiction since A is bigger than minus S, so we get that minus A is smaller than S. Again, by the changing sign flips the inequality. So minus A is smaller than S, but S is the smallest lower bound, upper bound. Of A. And this shows the claim. So again, go briefly through this once again. We have used the existence of a smallest upper bound, show that minus of this number is a lower bound for A. Then have assumed that there would be a bigger lower bound, but then by the sign flipping method we show that minus A would then be an upper bound of minus A, which would be actually smaller than the upper bound S, but S is by assumption, by definition, the smallest upper bound. So this cannot exist, and this gives the contradiction. So this implies that such a lower bound A, which has this property, cannot exist, and we have proven the claim. So this is indeed the biggest lower bound. Okay, so much for the existence of biggest lower bounds. Now as the next thing, I will do some additional terminology. Unfortunately, it's kind of unavoidable to have a lot of new definitions and terminology in the beginning. Namely, this time we only consider subsets of R. So from now on we will mostly work with R and later on with the complex numbers, but not with general ordered fields anymore. So for A bounded from above, denote its smallest upper bound. I just want to give it a name because this number appears quite often, by sup A, and we call it the supremum of A. Same thing with the biggest lower for, before I proceed, one more thing. If A is not bounded from above, then we just say that sup A we define as plus infinity, so the infinite symbol, which I haven't formally defined, but I hope you know what's meant by this. Part B, same thing for the lower bounds. For A bounded from below, denote its biggest lower bound by inf A, and this number is called the infimum of A. So for A not bounded from above, from below, we just put inf A to be minus infinity, which is again a little imprecise since I haven't formally defined this, but anyway, so this is just notation so far. Okay, the infimum. Then two special cases. If the supremum of A is actually an element of A, which we so far don't know. We have only seen by definition that this is the smallest definition not here anymore, but the smallest upper bound, this just has to be some number in R, but we don't know if it's in A. It's just some upper bound, which doesn't necessarily have to be in A, period. And if this is the case, if this is indeed an element of A, then call it the maximum of A. This is, for example, the case if we have a finite set, a finite subset of R, then the biggest element will always be the maximum of a set. Denote it by max A. And the same thing, now you can probably guess what I will write down next. If the infimum lies in the set A itself, we call it the minimum. Call it the minimum of A, and denote it by min A. So it's always necessary to distinguish between minimum and infimum, and the same between supremum and maximum. So one should easily talk about the maximum of some sets, because this might not exist. So if this is not the case, we say that the maximum or the minimum doesn't exist. Okay, so to get all this terminology right, I'll give you a very simple example. So example 147. We consider the following subset of R. Let I be the set of all x in R such that 0 is smaller than or equal to x is smaller than 2. Very simple set. Okay, what can we do? One shows, I will not carry out the details and leave this up to you. One shows that. So what are the lower bounds and upper bounds? So we know that every negative number is a lower bound. Of course, every number in here is non-negative, so they will be bigger than any negative number. And we know that every element of the set is bigger than 0. And we can see that any positive number would not be a lower bound, because 0 is inside this, lower bound, because 0 is inside the set, so we cannot go higher than that. So one shows that the infimum of A is 0. And since 0 itself is inside the set, we get that the minimum of A is 0, just by definition of the minimum. Now for the other side, we see that it's bounded from above by 2, because everything here is smaller than 2, so especially smaller than or equal to 2. So every number bigger than 2, which will definitely be bigger than the supremum, so 2 is our candidate. And we can see if we take any number smaller than 2, we will always find something in the real numbers. We will make this precise in the theorem later on, but we will always find something that is bigger than this, because we can kind of go arbitrarily close towards 2. This means 2 is our supremum. But as you can see, 2 is obviously not an element of the set. So this time it's really the case we have the smallest upper bound, which is not, oh sorry, I've written A, of course, let's call the set A, I'm sorry about that. Sorry, just notation. Sorry, the supremum of the set is 2. So 2 is not inside the set, and so it cannot be the maximum. And this is really an example where the maximum doesn't exist. So max A does not exist. And this really shows that the supremum does not necessarily always have to be in this set. So this is something that might happen, that the smallest upper bound is not part of the set. Okay, so much for that. Now some further result on real numbers, which is something I want to state without proof, because I could do the proof now, but it's actually not that easy and quite long. And there was kind of a shortcut I can use later on, so I will postpone this proof to a later point in the lecture. But don't forget about it, I will prove this, I promise. Let A be a real number which is non-negative, in the sense of ordered fields here. So non-negative real number, and let n in n before we had this problem that some equations like x squared is equal to 2 have no solution in the rational numbers. And we want to show now that this is in the real numbers is not the case, and especially the following holds. If we have so some non-negative number and some a, then there exists a unique even solution of x to the n, so x is a real number, sorry, this is something I have to stress. So some real solution of x to the n equal to a, and it becomes unique when we demand that x is non-negative. So this thing has a non-negative solution, and this is something that looks probably pretty familiar, namely this is the nth root of a number. So this says that all non-negative real numbers have roots, so we have to kind of show the existence of roots now at this point. So the proof of this, again, I will do much later, so I don't know how much, but proof later. But I want to, again, introduce the terminology for roots so that we can use them in the future. So, and basically I'm now bringing back high school notation, but putting it in this groovy framework of real numbers and ordered fields. Let A in R with A non-negative and N in N, and this unique solution here, the unique solution of x to the n equal to a, which is non-negative, is called the nth root, root of a. And we denote this, as we know from school, denoted by this root symbol with an n on top, nth root of a, or as we can also do a to 1 over n. So we can now introduce these exponents here. This is additional notation here. And in the case n equal to 2, as we know from high school, we usually put we denote this just by root without leaving out this 2. So this would be the second root here, and this is then called the square root of a. So we've already constructed our nice roots of numbers. Okay, let me quickly erase. Okay, with roots we have now defined powers with exponents 1 over n. And we had before powers with integer exponents defined, and what we do with these two things is now to technically define powers with rational exponents. The real exponents will come later, but so far we can do the following. For p over q in q, so some integer on top and a natural number on the bottom, and a bigger than or equal to 0, put a to the power p over q, we just define this as taking the qth root of a, and then, so this is what we have defined, q is a natural number, and then take the pth power of it. This is an element of R, and so this is again multiplication in the field R. So we can formally define this power, right? So this would be the qth root of a to the power p. Okay, so speaking of q, I have previously introduced natural numbers, integers, rational numbers just technically and formally, and now I have introduced the real numbers in this weird way of this complete ordered field. So, of course, we want n, z, and q to be subsets of R and to be a whole part of the whole story. And this is what I want to do next, to show you how natural numbers, integers, and rational numbers then appear again as subsets of R. So, next aim. I want to redefine n, z, and q, which I haven't really properly defined yet, as subsets of R. Okay, definition 150. This is now a very formal definition. So the problem is now in this standard way of constructing the real numbers as a complete ordered field, I don't have natural numbers in there. I don't have 1, 2, 3, 4, 5, and so on. But it's not true. I have a 1. Namely, 1 is the neutral element of multiplication, which I have in any field. So 1 is actually something which I can define in R. And this is precisely this unit, this neutral element of multiplication in R, called 1, which I want to use to define the natural numbers. Namely in the following way. And this is now a bit technical, and we will later see why this is just a kind of useful thing that I will use only this next construction in this section and the next, and then it doesn't matter anymore. But, or shouldn't matter anymore, anyway. So, first of all, let again 1 in R be the neutral element of multiplication, which exists in any field. A subset of R, a subset M of R is called an inductive subset if the following holds. First of all, 1 lies in this set, and secondly, if there is a real number which lies in the field, then I want that x plus 1, this is just addition in the field, this is the neutral element of multiplication, I want that x plus 1 is again in my set. Okay, and we want the natural numbers to have this property. We want to have 1, we want to have the number 2, 3, and which are supposed to be always taking this, adding 1, adding 1, adding 1, and so on. And so we get the natural numbers. But formally, we can define this as follows. Define the natural numbers n as a subset of R by the following. Oops. We can describe this as a set as n is to be defined as the set of all x and R, which lie in every inductive subset. X lies in M for all inductive subsets M of R. This could also be defined as the intersection of all inductive subsets of R. That's another way of putting this. So it turns out that then if this is, because this is in all inductive sets, it turns out that n is, I mean this is kind of trivial from the definition, n is itself an inductive subset. So the most sophisticated definition of n you can think of. And to put it as a remark, one checks that just from this definition, which is not very insightful, that we can actually define that n is then in this way given as follows. We have the number 1, which is a neutral element here. Then we have the number 1 plus 1, which we call 2. Then we have the number 1 plus 1 from before and add 1 again. And we can do the same over and over again. So we always add 1 to the number which was previously in this set. Okay, and then we get this. So this number we can then call 2. This number we can call 3. This number we can call 4, and so on. So the number n we would actually get as n times adding up the 1 with itself. And of course, since the field addition here is associative, we could actually leave out the brackets because they doesn't matter the order here of addition. Okay, great. Yeah, so this is how we kind of call these different numbers. Okay, first of all, one important property of the natural numbers that we want to check. Again, this is some kind of a sanity check theorem. There's a property which is kind of natural, but of course not trivial and not obviously following from everything. Namely, the n as a subset of R is not bounded from above. So we get infinitely big natural numbers. And this we can now prove using this defining property as the set of elements which are in every inductive subset. Whoops. And we do this again, we prove by contradiction. We assume the contrary, we assume it's bounded from above and bring it to a contradiction. Suppose n was bounded from above by some number s in R. It was bounded from above. We don't want s to be an arbitrary number. We want s to be the supremum then, because we know it's part of the real numbers, and the real numbers, we have the existence of smallest upper bounds, which means of suprema. So assume we have this supremum of n as an element of R, not infinity. So then we know, since this is the supremum, this is the smallest upper bound, this means that s minus 1 is not. So we subtract the neutral element here. This is not an upper bound of n. So what does this mean? This means there exists an n in the natural numbers with n bigger than s minus 1. Okay, but if we have this, we can now again use this theorem 138 with these properties of ordered fields. We can just add 1 on both sides of the inequality and nothing changes. Since we have, this is not theorem, this is ordering. This is ordering axiom 01. If we add the same thing on both sides, the inequality stays the same, basically. So, yes, and for strict inequality, it was the theorem indeed. So, but yeah, anyway, sorry. If we add 1 on both sides, we get that n plus 1 is bigger than s. But since n element n and the natural numbers is inductive, the set of natural numbers is inductive, it follows that n plus 1 is again an element of n, just from this formal definition by being this inductive set. So this already is a contradiction. Since we have shown that this holds, but we have assumed that s was an upper bound. So this is a contradiction. Since s is an upper bound. Of n. So this implies we cannot have such an upper bound. So if we have an upper bound, we would have a smallest upper bound, and we just have shown that this leads to a contradiction. So this means n is not bounded from above. Okay, this is a very important property of n. This has a nice consequence, a very little thing, but which is interesting to see, and which we will also need later on. Corollary. I think this is the first corollary I'm using. A corollary is something which is, again, a mathematical result, a statement, but which kind of is an easy consequence of an earlier theorem. So it's not kind of, we don't need a big fancy proof, but we can just use a previous theorem to derive this. So if this directly follows that, then we call it a corollary. Okay, and the corollary of this result is, for every epsilon bigger than 0, this is the first appearance of the famous number epsilon, which will appear many, many times in this lecture, and is always supposed to denote something small, so some small positive number. And we get that for all positive numbers here, for all can be arbitrarily small, there exists a natural number, n in n, such that 1 over n is smaller than epsilon. So for every tiny, tiny, tiny epsilon, we can find the number n such that 1 over n is even smaller. So 1 over n can become arbitrarily small if n becomes very big. This is something we kind of intuitively know, but this follows here from that theorem. namely by theorem 152, if we have some epsilon, there exists an n in n with n bigger than 1 over epsilon, because natural numbers can become arbitrarily big, so 1 over epsilon is not an upper bound, and so we get some number which is bigger. So, but if we have this one, and this was part of this infamous theorem 138 with all these properties, I will not all the time give reference to this theorem, but just for this section, maybe the next one, to be a bit more precise, this was part H of the theorem. Then it follows that taking inverses, then we also get an inequality, but the opposite one. Namely, then we get 1 over n is smaller than 1 over epsilon, but we have seen in the theorem, which I haven't mentioned here, that the double inverse is again the element itself. And this is what we needed to show. So that's why it's a corollary, because the main thing is just that we find such an n, and then it's just a very small way to derive this. So we can get arbitrarily small fractions, which is an interesting thing. Okay, or arbitrarily small inverses of natural numbers, to be precise. So we have studied the natural numbers now, and now it's time to introduce the integers and the rational numbers into the discussion. So the integers as a subset of R are defined by the following. Z is defined as the following set. We take n, which we have just constructed. Then we take the neutral element of addition, which we always denote by 0. And then we take all additive inverses, to say it in a posh way, all additive inverses of these natural numbers, which means we take the union of all, the set of all x in R, such that minus x is in n, to be very formal. So this is then the part of the negative numbers. Okay, and additionally, just for notation, because we will need this later on, I will denote always by n0 when I want 0 united with n. So if I want them to exclude 0, I will denote this by n0. Be the set of non-negative integers. Okay, next up are the rational numbers, and I will just erase the blackboard. Part B, we will define the rational numbers, and now that we've got the integers and the natural numbers, we can basically use the informal definition I gave before for the rational numbers and use this for a technically clean, precise definition as a subset of R. Namely, the rational numbers Q as a subset of R are given by Q, defined as the set of all, and now we just take an integer m and multiply it, this is field multiplication of R, with the inverse of n. And this is what we denote by m over n. So this is m over n is defined as this technically. This is an element of R, where m is an element of z, and n is an element of n. So in this way, we now have a formal definition of the real numbers inside the of the rational numbers inside the real numbers. Okay. Yes. So to proceed, I'm going to leave some space here. Okay. I will add something here later on. So the rational numbers. We know from high school intuitively that the rational numbers are a very big subset of R in a certain sense, because every number of R can be approximated by rational numbers, and this is something we will not formally prove at this point, but this is really the fact that the rational numbers are somehow always inside of R. The technically correct term would be saying that it is dense in R, but this is a notion I won't discuss in this lecture. But what we can now see to formalize this, that the rational numbers are basically everywhere in R. If we take two real numbers such that x is smaller than y, then in between x and y there is always a rational number. Then there exists a rational number q inside of q with x is smaller than q is smaller than y. So always in between those things. So the numbers can be arbitrarily close together. If they do not coincide, we'll always find a rational thing in between. And to prove this, I need some notion that I need to define at this point. So I just change the ordering here to make it more comfortable for you to get the idea. For x and r, we put this is called as a floor function, or just in German you call it Gauss bracket. This thing here of x, so I would just call this floor of x. The floor function of x is defined to be the biggest integer, so the supremum of all n in z, such that n is smaller than or equal to x. So if you imagine the real number as a number with infinitely many decimal digits, we just cut away all the digits and just set them all to 0. This would be what happens here. So the biggest integer that is smaller than or equal to this number. Okay, and I will now use this notion here in the proof of this theorem. So how can we do this? This is always, of course, an integer. That's important in this point later on, in the proof here. First thing, if x and y are quite far apart from each other, namely if the floor of x plus 1 is still smaller than y, then it's very easy. Then we get the rational number for free. Namely, we can just put q to be the floor function of x plus 1. This is an integer, and the integers are in the rational numbers. So, we've already done the job. Of course, this number here. Then we know that x is smaller than q, because if x would be, if x would be at least 1 bigger than this floor plus 1, then we could add, this number wouldn't be the smallest one. So this can only differ from x itself by at most 1. Otherwise, we would always increase this integer, right? So we know that this has to exceed x, otherwise this floor wouldn't be well defined. And by construction, this holds. So this q really has this property that we want. So now we come to the other situation. Assume now that this doesn't hold, and this means that x is smaller than y, and y is smaller than the floor of x plus 1. So this would mean they're quite close to each other. So first of all, by the previous corollary 153, there exists a natural number such that 1 over n is smaller than the difference of y and x. We know this is a positive number, and so we can find some n such that this fits neatly. This is small enough smaller than the difference. But then we consider the following. We define a number called m0, and we put this to be the biggest integer, the supremum of all k in z, such that the floor of x plus k over n is still at most x. So we know that the floor function of x is smaller than x, and we have now so of course we might even add 1 over n and to get somewhere, but we know that this supremum here is finite. This is an integer, because this k cannot be bigger than n. If it was n, we would have 1 here, and so for the same reason as before, by definition of the floor function, this inequality couldn't hold anymore. So this is indeed well defined. So we get this biggest number such that we still stay inside of x, and then we go one step further. We put m to be m0 plus 1. Then we know that if we take the floor of x plus m over n, we would jump over x. This would be bigger than x. And this is what we do now. We consider q, the rational number we are searching for, to be the floor function of x plus m over n. This is the rational number, this is a rational number, and so the sum is again a rational number. This is in q. So, as I just said, by definition of m, we get that x is smaller than q. Okay, but also, moreover, q is, by definition, the floor of x plus m over n, and by definition this is plus m0 over n plus 1 over n. This is just how m was defined. And m0 is just defined in this way, such that this here is still smaller than x, smaller than or equal to x. So this, by definition of m0, is smaller than or equal to x plus 1 over n. But we have chosen 1 over n so small that this holds. And if this inequality holds, this means that x plus 1 over n is smaller than y. Sorry for messing up here. Yeah. Hope still readable. So this is smaller than y. So this means this here is smaller than y. So we have found our rational number. We have found q as a rational number, which is bigger than x, smaller than y, and this is what we wanted. Yeah, this shows the claim. Okay, so we have now shown this property of the rational numbers. This should conclude the first discussion of real numbers. We will extend the numbers even further to complex numbers in 2 sections, but before I want to introduce some mathematical proof method, which is now using the structure of natural numbers in a certain way, the so-called mathematical induction, as we will see in the next video, and I look forward to seeing you there.